Okay, so last time we were looking at the matching polynomial. We showed that it is, so we looked at a slightly different form, which is this kind of form that, so you have a variable x, and then you have a match, you have m matching. And we showed that this polynomial where you have x to the power 2 times size of matching times minus 1m for every matching. So which becomes in the univariate case, minus 1 to the power k, ak, x to the 2k. This thing is real rooted. Okay, so we showed that that is the case. And from this, we wanted to somehow now argue about log concavity of matching numbers. So that's a simple argument. We didn't do it last time, but just the point is, the only issue is that, so if you look at these quotients carefully. So the point is that all the, so really I should write it as, so like you see, if you write it as a polynomial, then all the odd coefficients are actually 0. So the log concavity by itself doesn't tell you much right now, right? That's the problem. But that's easily fixed. So the point is that, so we have mu gx, which is equal to summation k from 0 to n by 2. So this is the size of matchings, minus 1 to the power k, ak. So ak is the number of matchings of size k. Okay, times x to the power 2k is real root. So now let me consider a different polynomial, which is, so the polynomial that we actually want to look at. And that polynomial is, so consider pg of x, which is defined to be let me just call the variables differently. ak, y to the k. So this is the actual generating polynomial. So if we can prove that this is real rooted, we are done, because then the log concavity just follows, right? Because now the coefficients are correct. So is that clear? So all we have to prove that this guy is real rooted. Okay. So, but what is this mu g of x? So notice that pg of y is nothing but mu g of I square root y. So okay, so this I have to be a little bit careful writing on, because I'm writing on a square root. So for every complex y, and so the point is, what is the square root? What is the square root of a complex number? So it's not a single valued function, right? In that sense, so there are many ways to get around this. I will just say that you just take any one of the square, and root y is any solution to
Piyush, why are we not taking PGY with the minus 1 to the k coefficient included?
Yeah, that also I think will work. Yeah, that also will work. Yeah, that should also work, because the point is that yeah, the minus sign will cancel out in the log concavity. But let's just do it this way, so that there's no difference.
Yeah.
Yeah, I think that should also just work. I mean, the point is that, yeah, I mean, they're related, right? Because if one is related, the other is also related. That they're related by a change, like that polynomial is just this polynomial evaluated minus y, because that alternates the signs.
That I substitution won't be there, right? That's the difference. That iota.
Yeah, but just look at, so the polynomial that you are considering is this qgy, which is a to the k minus 1 to the k y to the k, right? But that's exactly pg of minus y. So any one of them, I mean, if one is related, the other is also related.
Okay, yeah.
There's no. Okay, so but yeah, so now how do we? So suppose t is such that pg of t is actually 0, and then mu g of I root t is also 0, right? But this implies that I root t must be real. right? But what does that mean? That means that square root t must lie on the imaginary axis, right? Including it could possibly be 0, but it also lies on the imaginary axis. Right? So its real part is 0. Okay. So is this fine? So let me just. Okay. So we have this much. So this must lie on the imaginary axis. But that means that t must lie on the real line. Because right, so if root t lies on the imaginary axis, square must lie on the real line. So this implies that PG is also real root. And so from previous lemma, the sequence AK is ultra log concave, right? So in particular, AK square is bigger than AK minus 1 plus AK plus 1. This is a non-trivial fact, right? I mean, this is not obvious from the very beginning that the number, like if you look at the number of matchings of a given size and indexed by the size, and then this sequence is ultra log concave or even log concave, or that even that it is unimodal, sort of not. So yeah, so there is a so this is one proof. So actually, yes, we have ultra log concavity. For log concavity, can also be proved directly. I mean, yeah, you would imagine like the commutative argument by trying to set up a injection between the two product sets. Like trying to set up an injection between the like size of matchings. So matchings of size k times matching of size k to the set matching of size k minus 1 times matching of size k plus 1 can be proved by an injection argument also. So I think the first such proof I know is in injection argument also. But the first proof is by this, and I think this is so Heilman and Leaf proved this. I don't think they explicitly mentioned this fact, but certainly, I mean, I'm pretty sure they knew it. And I think there's this famous book called Matching Theory that has this and so on. But the injection argument, I think the first appearance is this in this approximating the permanent paper of Cherem and Sinter.
So what are the consequences of this? Like, do you get some Gaussian concentration of the size of a random?
Well, so one thing. Yes, why would approximating the permanent thing would be they would be interested in this is because it tells you that if the number of it tells you like it gives you a so suppose that you have a graph in which the number of near perfect matchings of size just like one less than the highest size is not too much larger than the number of perfect matchings. Okay, so that factor is bounded. Then you get that these factors remain bounded at every level, like right, because this thing can also be written as AK over AK minus 1 is bigger than so or rather let me write it this way, that AK minus 1 over AK is less than AK over AK plus 1. Right. So if the number of near perfect matchings is not too much larger than the number of perfect matchings, then you have this ratio bound at every level. And this can, so basically this tells that if you have an algorithm, so using this you can say that if you have an algorithm for sampling perfect matchings in a graph where the number of near perfect matchings is not too high, then you actually have an algorithm for sampling matchings of any size in such graphs. So that's one consequence.
So sorry, Piyush, this just gives you one way, right? So you said suppose the number of matchings because the left hand side is upper bounded by the right hand side, right?
Yes, that's only the one side is needed. Yeah. So the point is that if that number is polynomially bounded, then every number in the series is also polynomially bounded. I mean, so the point is you only sort of need the one side because the higher matching is which is the one that is less likely to happen. I mean, so
yeah, okay.
But isn't even then like AK minus 2 over AK plus 1, wouldn't I have to worry about that ratio?
which one?
Like AK minus 3 over AK or AK minus 2 over AK.
No, but the thing is, what they do is they get you a Markov chain for so you need some details. So what you have to do basically is like you keep on learning the ratio. So the ratio is polynomial. You actually keep on learning it using Markov chain sampling, and because it's big enough, you can learn it. And then you do a weighted sampling with an appropriate weight to learn the next ratio, which you also know is bounded. And then you learn the next ratio. So you keep learning all the ratios iteratively, starting from the top. That's all. Yeah. So we can get that. That will become a Markov chain thing. So yeah, but this is the crucial thing that even allows this to be done. Otherwise, it would not do this.
So you're saying, in general, log concavity helps estimate. I mean, helps this sort of approximate counting.
Yeah, it can. Yeah, so it can help because if you have an approximator for the top thing, you can somehow bootstrap it sometimes to just get things. It's not a direct reduction.
This is a standard known procedure.
Yes, yeah, sort of.
Okay.
I mean, yes. So how general the procedure is unclear to me exactly. But yeah, the thing is that without this, it would not work even for matches. That's what I'm.
Oh, so you require some other properties about matchings that makes this possible.
It's not about matching, but about the algorithm that you have for matchings, that you can do sampling of matchings. You can also put weights on the matchings, which depend upon the size and still do the sampling. So if you have those two things, you will get through. So basically the thing that works is that they don't just sample matchings. They also have a way of like sort of sampling matchings with appropriate weights. So the matchings. Okay. So here is what. So let me just say exactly what. So they get an algorithm that can do the following thing. It can sample matchings, not perfect matching. It can sample matchings, but even under the setting when you can put a weight on every matching, where the weight of a matching is lambda raised to the power the size of the matching. And you can do this as long as lambda is polynomially bounded. So they give a polynomial time algorithm where the runtime is polynomially dependent upon lambda, which will sample from a distribution which is weighted in this way. So is that
kind of weights are this sort of statistical physics kind of?
Yes. But the point is that they can do it for quite large lambda, as in particular up to polynomially large lambda. Okay. So now what do they do? So now suppose that your graph has the further property. So you have just this algorithm. So right now your black boxes, you have an algorithm that will sample matchings for you, where the weight of a matching is lambda raised to the power the size of the matching, and lambda is allowed to be polynomially bounded. Now what do you do? So now suppose you have a further condition that the size of the highest match, the number of like largest matchings is not too much smaller than the number of near largest matchings. So AK minus 1 over AK is just a polynomial. That's or rather let's say the highest matching size is M, then AM minus 1 over AM is at most a polynomial. Suppose you have this condition. This condition is satisfied by some classes of graphs like the extremely dense graphs and so on. But suppose you have this property, then what they say is that using this, you first take this lambda thing, and you sort of you can tune the lambda now to put a very high weight on the perfect and near perfect matchings to actually estimate this ratio, which you know is bounded, but you actually get a good estimate of this ratio, and then you use that to estimate the next ratio, and so on. So using this, you can get actually all the. Not just the top, I mean, using just an algorithm which is sampling matchings and this extra assumption that the perfect and near perfect are bounded, you can get sort of all the actually the as you go there, but yeah, you can get all the ratios starting from the like A2 A1 is easy, A3 A2 is easy, but as you keep on going, you actually need a sampler to keep updating this lambda until you get to the AK minus 1 over AK.
I see. No, but I was just saying, so, I mean, I don't want to distract you from the, but this might be sort of relevant, right? I mean, so.
Yeah, this is general. So this, what I told you is general. So if you have some distribution on any kind of objects, like where like, so let's say there are k objects of type AK and this AK sequence is strongly is log concave. So you have this property. Plus you have a sampler from these objects where you can sample where the weights are like lambda to the k. The object of size k gets a weight of lambda to the k. If you can do this for lambda polynomial, and if you also have the property that AK minus 1 over AK, the top guy is inverse polynomially bounded, then you get a sample. You can now use such an algorithm, your weighted sampler, to approximately count at all levels. You can approximate each of the AKs.
I see. I see.
So that is it.
I see. Sounds interesting. Okay.
One more question, Piyush. So, is the concentration just coming for free from ultra low concavity?
So what concentration?
So the random variable.
But I don't know what we'll say about matching. So what kind of?
You had earlier said that if a sequence, like for the Bernoulli case, because the coefficients are ultra log concave, you get Gaussian like Chernoff bounds just from the fact that these things are ultra log concave. Would you get that for a size of a random matching, that it is concentrated?
Oh, yes. Okay. So the thing is, yeah. So what did I say there? Yeah. So if it is real rooted and all that, so we saw that this is some of Bernoulli's, right?
Mm-hmm. Yeah.
And yeah. So now the question is, what are these Bernoulli's? Like some of them might be very. Yeah, so the concentration you'll get will depend upon that, right? So. Where the roots are. So yes, right is very quickly we'll actually get to the points of what the roots are, and then from that I think you can get some concentration.
Actually, it is also known that for a deregular graph, the roots are less than 2 square root k minus 1.
Exactly, that's the next thing I'm going to do.
So that will give concentration. Right?
Yeah, that will give concentration using just Hobding inequality and the fact that it's the sum of independent Bernoulli. But more than that might also be known. I don't know.
Okay.
But what concentration you get does depend upon the location of the roots, right? Because remember that the roots determine what the parameters of those Bernoullis are, and that goes into the Chernoff for our thing. Okay. So I mean, in particular, the roots might depend upon n and all. Yeah, they don't. So we'll see that. So not even regular graph, you'll see that any graph of degree, you can get a good bound on the root if the degree is at most d. That's the next thing. Okay, so any questions about what we have done so far? So the matching polynomial is real rooted. The matching polynomial we used was this version, minus 1 to the k, ak, x to the 2k. From that, we got to maybe the more reasonable matching polynomial is also real rooted, and from that, we got our one combinatorial result.
So Piyush, one further question. Sorry, this is about, like, I was just wondering, do ultra log concave sequences also have concentration, or that is not necessarily true? Like
I don't know actually. Yeah, I mean, it's not so. So what does it mean? I mean, like.
So you have these coefficients arranged in an order, and you can say that most of the mass, since they are unimodal.
Yeah. So this maybe you can get something just from the. I mean, apart from the definition, I don't know what more you can do, but I have not tried it. So.
Okay.
Sorry. Here, what was Siddharth and you meaning by this? Concentration? Sorry.
No. So the thing is, so what he's saying is that, like, look at this polynomial pk. It has non-negative coefficients. It is real rooted. Earlier we said that any such polynomial sort of comes as a generating polynomial of a sum of independent Bernoullis, right?
Oh.
So these coefficients are like the probability of those Bernoullis having certain values. So the sum, so it's concentrated.
I see.
That concentration depends upon where the roots are, right? Because that determines what the what the parameters of the Bernoullis are. So as Sriyato was pointing out, and as we will see soon, if a graph is of degree at most delta, then the roots of the not this matching polynomial, a slightly modified matching polynomial, can actually be bounded in on the real line. So using that, you can get some bound in P, and I guess that might give some concentration. I haven't tried it, so I don't know what it will give, but
I see.
That is one possible proof.
This is what you're going to do now, is it?
Yeah, I'm going to show that you can get bounds on the roots. So the next thing to show is that we have seen that the matching polynomial is zero rooted. Now we want to know where its roots are for graphs of bounded degrees. So that there are two reasons for doing it. The one is that it will be useful in one of the important results we'll see in the class, which is the construction of Ramanujan, or like proof of existence of Ramanujan graphs of all degrees. And other thing, it will introduce the notion of interlacing, which is very useful. Okay, so let's continue with that. So,
sir.
So,
hello.
Yeah.
Yeah. So you were trying to find the bound on the roots of that polynomial, right?
Yes.
So why not if we just consider the corresponding matrix form of this polynomial and try to bound the eigenvalues of the matrix by the Grasgorian theorem. There is a theorem on Grasgorian disks, which will give you the bound on the diagonals of the polynomials.
Wait, but okay, so you have to first come. So there are many things. So one is that you have to count with a matrix for which this is the characteristic polynomial. That I think we can do.
Yes.
Then you have to argue about eigenvalue bounds for that matrix, and I don't know if this might work, but the proof that we will see are actually much simpler.
Okay.
It's much more commentable. Okay, so for this we will actually look at a different roots of the matching polynomial, and this is directly from the Heilmann-Dietz paper. But I'll just simplify it. I mean, so they prove a slightly more more general results with weighted graphs. I'll just do it for unweighted graphs. So yeah. So I'll actually do the proof, but let's see. Okay, yeah, so we will not show interlacing, but we will do their proof of zero field source. So the roots of the matching polynomial, the Heilmann-Dietz theorem. So this is directly from Heilmann. So for this, we will actually look at a different polynomial, which is mg of x is summation k goes from 0 to n by 2 minus 1 to the k, ak, and here it will be x n minus 2k. So now these variables sort of are not sitting on the edges, but on the unmatched vertices. Okay, and the claim is that this is also real stable, is also real rooted. Why?
It is mu g 1 minus x into x powered n.
Yeah, so it's it's just x to the power n mu g 1. Okay, and we will bound the roots of this guy.
That's not a capital N, right? That's a small n.
Yes. Yeah. Something is wrong. Okay. So what? So now this is something that Siddharth was also pointing out earlier, that all these graph polynomials usually have very nice recurrences in terms of simple graph operations, like you remove a vertex, contract an edge, that kind of thing. So this one in particular, the good thing is that you can easily think of a recurrence in terms of So let's see. So it's easy, right? So let's say, so I have mgx on a graph. What is one smaller graph I can use? So take a fixed vertex. So let's take the vertices of G be v1 to vn. Okay. So what are the matchings? So thing is that I can say first I will count all the matchings in which the vertex x is not, vertex v1 is not matched. What is the total what is the total contribution to the sum of those matchings?
mgx minus v1 into some sign.
Sorry, matchings where v1 is not matched. Plus I bigger than equal to contribution v1 vi is matched.
Look, Piyush, I'm a bit confused because you have here a univariate polynomial, right?
Yes.
Yeah. So now what do you mean by, when you're just sort of, oh, but the AK still, the AK still represent the
Number of matchings.
the number of volts. Yeah. Okay. Good.
Okay. So so what is the first term? What is the contribution of matchings that where v1 is not matched?
Minus mu g v1. G mu mg g minus.
No minus, because the number of edges is not changing, right?
Okay.
Right. So the size of the matching is not changing. It's not matched. And remember that every unmatched vertex is contributing an x factor. So the first term is just x of m with on this removed x. Yes. Now what about this? What about the contribution where v1 and vi are matched?
The second term should be v1 to vi are matched and vi plus 1 is not matched. Right?
I mean, no. I mean, if v1 is matched to vi, I mean, I'm just breaking.
Oh, okay. Sorry. You said v1 is
where v1 is matched. Either it's not matched or it's matched to one of the other.
Yeah.
Okay. So suppose yes. So let's say it's matched to some vertex. So then what is the contribution to that?
So delete those two vertices and some x square into. No, not
1
x
over.
square.
Yeah. So no 1 over. So let's see. So if it is matched, it's neither of the two vertices is contributing anything, right? So this is just minus the sum. So minus because now I have removed an edge of m g minus v1 vi of x. Right? Assuming that v1 vi is actually an edge, right? So I should only go over the neighbors. Okay. If they're not neighbors, then the contribution is 0, right? That matching does not exist. Okay. Okay. So is this is this derivation?
We are doing something general like you do for generating functions, right?
Exactly. Yeah. So this is nothing. Yeah. So this can be done in a lot of cases. You can actually. I think earlier I asked this thing about chromatic polynomial there also. No, not in this class. Maybe in this class. I'm sorry. Yeah. So you can do this for almost any graph polynomial. Something like this usually works.
Isn't this the way we see that the chromatic polynomial is actually a polynomial? I mean, because that itself.
The chromatic
Exactly.
tells you that a chromatic polynomial will have alternating coefficients, alternating signs. But there it will not be this recurrence. You'll have to do this removing edge at time. So.
Can you just repeat why you remove the neighbors of vi also?
No, so let's look at this. So what is mg? So sum over all matchings, right? So remember we always had, this is also the same thing as m matching in g minus 1 to the power size n x to the power n minus 2. That's exactly what this polynomial is. So now I'm just saying, let us look at the contribution to this from those matchings where V1 is not matched. So in any matching, V1 is either not matched or it is matched to one of its neighbors. That's all it can do. These are all its possibilities. If it is not matched, what do those terms do? So those terms are just like a matching in G minus V1, except that the V1 will now contribute an extra X term, because each variable that is not matched, each vertex that is not matched contributes an extra X. So you get X times G minus. So that's the total contribution of those. Now, which other vertices can V1 be matched to? It can only be matched to its neighbors. Right? So let's suppose it's matched to Vi. Okay.
Yes.
So then what is the contribution coming from that? So then there's a minus sign, because that is one edge in the thing. Plus, we have to look at all the matchings in this graph that is G minus V1 Vi. You remove that edge from the graph, and you're looking at the matchings in the graph where V1 and Vi are not, because they can't be matched anymore. They've already been matched. Now, what can the other vertices do? That's what this polynomial is. Is it fine?
Yeah, can you just repeat why minus sign is coming out? You were saying.
Coming out. So remember, what's the thing here? So there's a total weight is minus 1 to the power of the size of the matching. Now let's look at a matching here. So the matching has one minus 1 factor for this edge V1 Vi, and then whatever comes.
I see. Yeah. Okay. Got it.
Okay, so now let me do some symbolic kind of manipulation, and let's see what happens. Okay, so just don't worry about some manipulations. Right now, don't worry about division by 0. Okay, so just think of them as symbolic. So just divide by this G minus V1. So what do I get? We get that mg of x divided by mg minus V1 x is equal to x minus summation mg minus V1 pi x over mg minus V1. Okay, I where pi is neighborhood. Okay, is this fine?
Yes.
Okay, so notice that this thing here and this thing here are of the same form. They're just like the same kind of function applied to a different graph. So what is this function? You take the graph, you look at the matching polynomial, and then you divide by a matching polynomial of a graph minus 1 vertex. Right? Wait, sorry. Yeah, and this is like the reciprocal of that. Right? So this thing here is sort of like a reciprocal of whatever is happening here.
Yes, but okay, I mean,
so not making any other claim, just that these two are at least somewhat similar.
They look similar, but the graphs might be different.
Yeah, but graphs have changed. Yes,
the graphs have changed.
Graphs have changed. Yeah. Okay. Okay, so now let's do a crude kind of argument. So suppose that someone had told us that for x greater than 2 times root d, okay, and any graph G of maximum degree at most. So let me call this delta and delta. Any graph H, it is true that mg of x over mg minus v1 x is at most true. Suppose someone had told us this thing. Sorry, H. Okay. Up to for all graphs of. So yeah, so I'm restricting now. So earlier I just told you that we were told for all graphs. Let me say for all graphs of size up to graphs up to k vertices. Okay. Can you now prove it for graphs of size k plus 1?
By the way, this is true for all I, right?
Yeah. For every VR. So yeah.
Yeah, it doesn't matter because it's for any graph. So yeah.
Yeah, V is, yeah. So when I say H minus V, I assume that V is actually in H.
Why induction?
Yeah, exactly. So the thing is that this thing already tests the induction, because now take then take G of size k plus 1, right? And then you have that mg of V, mg of G over mg of G minus V1 is equal to x minus this summation mg minus VV1.
So on the left hand side, you will have the X, right? I mean, it's a type.
Yeah.
There's a typo.
Huh?
No, I think on the left hand side you have a typo, isn't it?
Yeah.
Yeah.
Okay. Now this guy belongs to what? So it is it's a reciprocal of something that is non-negative. So it is
This is at least 1 minus delta, and there are delta many terms.
Yeah, wait. So just a second. I'm just making sure I'm not messing up something.
It's okay because you get 1 over root delta greater than, and then you have a subtraction. So everything is fine.
I messed up the inequality. Sorry. So I was told that. Sorry, I'm told that. Yeah, this is greater than equal. Okay. So okay. So now, so then this is less than. So this is between 0 and 1 over root delta, right? Each of these terms. If I am assuming that this is bigger than that, okay. But then what? So I want to.
So there are at most delta many subtractions.
Then we get that mgx over mg minus vx, which is x minus this summation mg minus v1 v2x over mg minus v1x. But where is the sum? So the sum is over v2 neighbor of v1. And this is between 0 to 1 over root delta. So this whole thing is bigger than x minus delta times 1 over root delta.
So,
right?
Piyush, I'm not. So, what if on deleting a vertex the delta changes
No,
for
but
the inductive?
good.
I didn't get the
So
question.
I'm
Can you
saying
repeat
that,
it?
so this is the point. So I'm saying that if the graph is of maximum degree, okay, yeah, you're right. So yeah, okay. So let's not worry about that. So right now,
But the
someone
delta can only decrease, right? So it will still be true. No, sorry, it's not.
yeah. So there's a problem, but yeah, let's see. So okay, maybe I am messing up something, but let us see. So this so all I wanted to claim is that this argument actually does. So if it was true for so if it is true for all the so if so yeah, so if it is if all these guys are bigger than square root of delta, um
Oh, I think you can pick the minimum degree vertex and delete it. So
yeah,
any.
so we're coming to that. But so right now, yeah, so right, I'll also have to improve this delta a little bit. But so yeah, so but the crucial thing I want to just say is that uh, so all I want to say right now is that this thing does seem to telescope like sort of dovetail in this way, that if x is bigger than some 2 times root delta, and if for all such x the ratios for smaller graphs are large, then the ratio for the big graph is also large. So right now there are lots of loose ends. So how, but as so the issues are right now, delta is
No,
changing.
no, I mean, like what Siddharth suggests, what is wrong with choosing the minimum? I mean, this V1 was arbitrary, right?
Exactly. So yeah. So we will. Yeah. So we'll actually do something slightly exactly the same kind of thing. So in fact, we will be able to use this to show that the roots also are. So yeah. So the roots are also within two, like, so the roots cannot be bigger than 2 times root delta minus 1 actually. So yeah. So we'll do. Yeah. So delta is also changing. What's the graph? Changes. Okay. So okay. So now, but let's notice one thing. So if for all x bigger than 2 root delta, it is true that this mgx over mhv minus x is bigger than root delta. Then you just by just sort of telescoping this, you get that this number is also positive for all these x, right? So there cannot be any root bigger than 2 root delta. If you keep doing this until you get to the smallest graph, right? And then you have that this ratio is always has the same sign for all these large x. So this polynomial always has the same sign for all the x that are bigger than this. Its sign doesn't change, which means that it cannot have any roots beyond 2 root delta. So
Sorry, Piyush, I'm a bit confused. So this was just to finish the induction, right?
yeah, so right now there are all kinds of mistakes here about like yeah. So I have to say what is the base case and so on. I just want to say why is this useful, and then we'll do it correctly now. Okay. So, but why is this useful? So, what I'm saying is that this actually does, if all of this was correct, it will tell us actually also that the root cannot be bigger than 2 root delta. So, why is this ratio important at all? The ratio is important because it is also telling us something about the root. Because what would this whole argument imply? It would imply that for all these large x, this mgx over mgv minus x is strictly bigger than root delta, and it's actually positive therefore. So you just multiply these things out and the telescope. So you get that mgx has the same sign for all these large x. Right? And is that fine? So you
I mean, you're saying assuming
it's true for all smaller graphs.
yeah, assuming so you're just telescoping the left hand side, you're continuously multiplying, right? So that you get your
Yeah, and I'm continuously multiplying positive things.
positive things.
So
That's all you require.
yeah, and the final polynomial might be negative or whatever, doesn't matter. The whole point is that all this tells us that mgx has the same sign for all x bigger than 2 root delta. Its sign doesn't depend upon x.
No, only for x greater than 2 root delta, right?
Exactly. Yeah, for x bigger than 2 root delta, its sign doesn't depend upon x. So which means that there cannot be a root after 2 root delta. Because if there is a root, the sign must change.
Sure.
Yeah. So I mean, it should at least go to 0. So yeah. So that's the point for this argument. That this argument is actually, let us correctly done. This argument let us show that we also have a root bound. And actually, we will show it for 2 root delta minus 1, and that will be done by just choosing these vertices correctly. Okay, so let's do that.
Piyush, just one in this telescoping cancellation argument that you were saying, won't you just get that mhx itself is greater than delta to the n by 2, like without any?
Yeah. This will you will get that also. I mean, the thing is, there'll be this final m1 thing, which will have some value. Yeah, but it doesn't. Yeah, so for the root thing, it doesn't matter. All you want is that it is positive. So do delta times n minus whatever, root delta times n to the power n minus 1 times whatever the final polynomial is, the final constant is. So I think it's maybe n or something, whatever. Yeah. But the point is whatever it is a fixed sign and it's not 0. And okay. But by telescoping these ratio bounds, we should be able to get that the sign of mgx for x greater than 2 delta remains the same. Implies no roots above 2 root delta, and by symmetry also no roots below minus 2 root delta, because it's a. So now let's do the argument regression. So let's do it.
Why is this a good thing, Piyush? That's I thought it is better if the roots are further away from 0. Is this the?
Well, I mean, why?
No, so okay, I'm asking, is this the statement we want to show, that the roots are closed in a disk? Or I thought you wanted to show some disk will be root free.
No. Well, I mean, depends, right? I mean, like we have done a 1 over x transformation already.
Oh, sorry.
But in any case, yeah. So all of that depends upon the thing you want to do. For this particular application, which is this Ramanujan graph, actually this will be the useful thing, that you have upper bounds in it.
Okay.
No. So what is the point?
So there's some other counting applications where sometimes it's good to prove that there is some polynomial you have and the roots are far away from 0. So we'll probably get to that later in the class. So there's some counting algorithms which can then. So many polynomials are easy. So let's look at this. So okay, so what's the point? The point is, suppose we look at this mgx, right? And mg0 is what? mg0 is pretty easy, right? It's like only a0 survives, which is just a monomer. So it's very easy to compute. And suppose that all the roots were also far away from 0. And I just wanted to compute log of m. So I want a multiplicative approximation to m. So if there are no roots of m close to 0, then log m is sort of an analytic function close to 0. So I should be able to approximate it by a small Taylor series expansion. And how large the Taylor series expansion has to be depends upon how far the roots are. Because the closer the roots are, the roots sort of determine how large the analytic, like how big the radius of convergence of a series is. Because when m gets a root, log m becomes non-analytic. So up till that point, you should be able to expand. And so the rate of convergence will also depend upon the distance to the radius of convergence. So this can be used to sort of approximate log of m by just taking few terms in the Taylor series. And for that purpose, if you want to apply this technique to a polynomial, it's good to take a point, like in this case 0, and show that there are no roots around. Very like up to some distance, there are no roots. And then using the fact that things are easy to compute at 0, you do the Taylor expansion, compute some terms, and get approximation for log n, which gives you a multiplicative approximation to n. Assuming that you can show all this, that the roots are fast, or Taylor series is converging fast, and so on. So for those applications, it's better to show that the roots are far off. And here we are doing the opposite. Here our goal is to show that the roots are not so far off. Right? So our goal is to show that the roots are actually at most 2. Actually, we'll show that it's 2 times square root of delta minus 1.
Thanks.
Okay. So yeah, so we'll show that. Okay. Yeah. So the only thing to do, as Kadevan pointed, is to do this carefully, not for all graphs. So yeah. So when you do this recursion, you have to take care that things are still fine and so on. Okay. So this. So let me actually just so not try to do this completely by myself and actually have the reference ready. Okay.
By the way, did you say this is also from that Heinemann and?
Yeah, this is directly. This is more or less directly from the. Well, not more or less. It's exactly there. So they just prove a more general result. That's the only difference. They prove it for weighted graphs. Just 1 second. Yes, this is the proof of file only. So yeah, so this the family that of graphs that we have is the following. So we'll have this. So just checking on this thing. So the family. So given a graph G is a family of subgraphs, not edge or vertex subgraphs, but just subgraphs. You obtain the following way. So exactly as the recurrence proceeds. and as follows is a family of pairs of subgraphs. That first one G minus V and G minus UV is in EG if U and V are adjacent. So the point is that these things can appear. So one of them on the left hand side of the recurrence, the other on the right hand side of the recurrence. So that's what this EG family is going to do. Okay. If U and V are adjacent. Okay. Second thing is that if if G prime and G prime minus V are in EG, then G prime minus V, G prime minus VU is in EG whenever UV are adjacent. G prime. Right? So U must be a different vertex in particular, and it must be in G prime, and V must be adjacent. So edges are not being removed. So yeah, so adjacent in G and U in G. So the same thing. Okay. And third thing. So if G prime minus V in EG is such that that V has no neighbors. No neighbors in G prime. So then choose a vertex U in G prime minus V. So that at least one of the neighbors of U does not belong to G prime minus V, and add okay, and then the so let's go over this as we do the proof. But the claim is that the following, that so the Hellman lemma is that if G is connected of degree at most delta. So they do a more general thing, but I'm just take it most delta. and G prime minus V is in EG. So this is first assumption, and second assumption, and third assumption is that x bigger than 2 times square root of delta minus 1. Then this q of G prime x divided by q of G prime minus V x is greater than root delta and q. Well, sorry, I'm using their notation. Sorry. Sorry, so slipped into the hiding element. Provided G prime is not equal to. Okay, so it's saying that for every pair, every such pair, so the lemma will be yeah. So you take every so this is construction of these pairs of graphs. How were they obtained? So you are allowed to remove so you take a graph and you remove one of the so basically these are the 1 and 2, they're exactly things that can appear. So the first component will appear on the left hand side of the reference, second component the right hand side. So think of it like that, and saying that for any such pair, if you have such a pair G prime and G prime minus V, so notice that it's always the case that the second element of the pair is missing one extra vertex, right? That was in the first pair. Okay, so it's always like that. So you take this, and it's saying that if you have such a pair in this set of graphs that is generated, and if x is at least 2 times root delta minus 1, then the ratio, the kind of bound we will want is also delta minus 1. Is this bigger than or equal to delta minus 1 is correct, and in particular, and also this mg prime is also positive. Okay. Okay. So
so mg prime of x being positive, that's also part of the consequence, is it?
Yes.
Then yeah, okay. Yeah.
Then okay. So provided G prime is not equal. Yeah, and then for G, of course, you just do so G, so once you have for all of these things, for G, you might get something slightly worse, right? Because now you have delta terms. So that's the only thing. So you will not get root delta minus 1, but the positivity will still have. So okay.
No, what did you say? So once you have this for
we will have this for all G prime that are not equal to G, and then we will apply the thing to G. So we will get some weaker ratio requirement on G, but the positivity is what we care about, and that we get. So the lemma is only for G prime not equal to G. When the first component.
After this, you will do that telescopic thing that you were.
Yeah. So yes, this also will include a telescoping, and then we will have to do one more telescoping for G itself. I mean, the point is that in this thing you will be able to choose these sequence in a way that you always have a delta. I mean, the degree is always delta minus 1, right? So at every vertex, because you have removed one word. Right. So I mean, like, remember, right? So in this, when we were doing telescoping, we're summing over all neighbors. So there will be delta such terms. Right? We only want to have delta minus 1 terms, and this we will be able to do because the way we are choosing these graphs, every vertex that is there in this, so the vertex on which we will apply the recurrence will always have degree only delta minus 1, because one of its vertices was gone because it's not equal to G, and all. The only way you're constructing these pairs, they all have one less degree at the top vertex. Okay, so we'll see that. So it's not so. So this is just to get the optimal thing. Okay. Okay. So what's the point?
Sorry, Piyush. One thing I'm a little uncomfortable is, like, you're saying of degree at most delta, but do you mean to say that here and delta is achieved. Some vertex has.
Yeah, so I'll say yeah. So actually, so let's say of degree. Yeah, so degree. Actually, I should say that correctly. So of max degree delta. Yeah. I mean, the thing is, yeah. So if you put something larger here, I will also be assuming something larger here. Right? So, like all of these things are only for x that are large.
Right. I see.
So this is important. Okay, so let's prove this lemma. No? So yeah, so the proof again we have to start with the recurrence. So and the point is that this mg prime of x over mg prime minus v of x is equal to x minus. Okay, so let me write it. Okay. X times n and minus the sum of u. U is a neighbor of v g prime of m g prime minus ub. Okay. And now the crucial point is that the crucial point is that if g prime minus p are in Eg, then the degree in g prime of v is less than or equal to delta minus 1. Okay? Because whenever this so just right? So look at this u, for example. So let's look at the first construction. Whenever you do this, so v is already gone. So one neighbor of this guy that you are subtracting from the first is always removed. So its degrees at most delta minus 1. Okay, so that be the case in this whole construction. Okay.
No, I'm a bit confused. So sorry, go to the last page once more, please. Yeah. No, the last thing that you. Yeah. So, so V was in G prime, right?
Yes. But how are these things generated? So let's look at these pairs, right? So let's look at the first one. How is this generated? So G prime is like G minus P. Yeah, so this is a bit confusing because V is now like this. So let's look at this. So the role of V is now being played by U because this is the word that you're removing from G prime. G prime is this, and you're removing U from G prime.
Yeah.
Look at what is the degree of U in G prime.
No, if you're removing U from G prime, why is the degree of U at most delta minus 1 and not, I mean, why can you say delta minus 1?
Yeah, so let's just see that. So let's look at the first thing here. So G prime is G minus V.
Yeah.
And I'm removing U from G prime. But how, when am I?
U was in the neighborhood of V, is it?
Yeah, but I'm only allowed to remove U if U was adjacent to this V.
Yeah.
So delta minus 1. Similarly here and similarly.
Yeah. Only if it's in the neighborhood, correct.
Okay. So then we get that also notice that the important point is, this is the first point. The second point is what is going on with this EG point. The point is that if this guy G prime minus UV, okay. So this is basically what I'm saying. It's G prime minus V, G prime minus UV is also in EG. So these are the 2 points crucial. Okay, and now you can do the induction. So with this, you just do the same induction as before. So with this, the induction can be, so we can prove the claim by induction. I mean, provided that G prime has at least 2, provided G prime has at least 2 vertices. I mean, yeah, otherwise you will just do it by hand. At least. Let me set as large enough. As you know, it has okay. So with this, we can prove the lemma by induction on the size of G prime, and by the same argument, so you just do this mgx over mg prime x over mg prime minus vx is x minus summation u neighbor of v and g and g minus u minus uv x and then g x apply. So is less than 1 over square root delta minus 1 by induction hypothesis. Delta minus 1 neighbors as G prime minus V. And this is greater than 2 times delta minus 1. So this whole thing is bigger than.
Sorry, Piyush, I have still just not getting able to wrap my head around it. No, but the point is, I mean, what you showed is the degree of the vertex V in G prime, that's less than equal to delta minus 1, right? But some other vertex may still continue to have degree delta.
Yes, but the only so let's see, only the degree of vertex V matters in the recursion.
No, when you apply the delta, when you are multiplying by the vertices of degree V, there it matters. But in that, I mean, there only the vertex, how many such things you need? Of course, the number of neighbors of V, but what is inside that? Why does, sorry, I mean, like, you know, this inside the sum, in the summand, what is in the summand, by induction, what you have is 1 over the degree of the graph G prime. Right?
No. So let's see. So what is the induction? So what is the induction hypothesis? So G is fixed in advance, delta is fixed in advance. Now, our induction is only on those. So after that, EG is also fixed in advance.
Yeah.
Okay. And all of these things are fixed. G, delta, EG are all fixed.
Yeah.
Now the induction is that for every pair G prime minus V in EG, so the induction is just on this part.
Oh, I see.
So fix G, fix delta. So this is the induction hypothesis. Fix G and delta in advance. Okay, so fix G, fix delta, define EG. Okay, by these operations. So the operations, yeah, you sort of with foresight you have defined it in such a way that it will contain all the pairs that you can ever generate using this process. Then, yeah, then you do this. Okay. There's no n prime, so this n. Okay. So after this, you can do the induction, and the only point to verify are these 2 points. So this is one of the important things, that this construction of EG is containing all the things that you will generate in this. So now the only thing is remaining, which is also easy, is that once you have this every pair in G prime, you also want to prove it for G, and that is just from the fact that after the lemma, note that M G minus V M G X M G minus V X is equal to X minus summation U neighbors of V M G minus U G minus U V X. So from lemma, we get that M G minus V X, it's positive for every X equal to root delta minus 1, and this quantity here is bigger than root delta minus 1 for every X equal to root delta minus 1. So mgx over greater than is greater than or equal to 2 root delta minus 1 minus, sorry, is less than 1. Yeah, so delta over delta minus 1, which is 2 times delta minus 1 minus delta. So yeah, so well, I mean, so it doesn't work for delta equal 2, but delta equal 2 you can handle by hand. Delta equal 2 just means that you have just paths and circles, and those are easy. Okay, so what have we done? So we have proved that. I also wanted to do interlacing today, but we couldn't do that. We proved that. G is a graph of max degree delta. Then G x greater than LVX greater than. This implies that G has no roots. In fact, even equal to, because yes. Symmetric about the origin of real roots of n. In fact, the proof shows that greater than equal to also. Okay. So, is there any questions about this? So we'll just stop with this. So this is
So this kind of argument can be useful for spectral expansion, right? Because you're just showing that the roots are in this interval, right?
yes. So exactly. So we will the reason for proving this is that we will use this to look at spectrums of lifts of two lifts and use that to give the proof. The Marcus Spielman shows the proof of existence of Ramanujan expanders of all degrees.
There was a proof of this just using spectral expansion, right?
Sorry?
There was a proof of this just using spectral expansion only, right?
Of what?
That in a d-regular graph, the matching polynomial has all roots less than 2 square root t minus 1.
But I mean, I never used expansion, right? So I'm just.
No, I'm not here. I mean, there was another proof. Right.
So, I mean, yeah, I mean, I guess one can, but the point is that the graph need not be an expander. This is.
No. So in a d-regular graph, I mean, it is matching polynomial is becomes the characteristic polynomial of a subgraph of its universal cover.
Yes, exactly. So this we will, yeah. So we will look at that connection next. Yeah.
Yes, I mean, there.
Yeah. I think I see what you're saying. So yeah. So the universal cover. So yeah. So the universal cover is just a fancy topological name for a d-regular graph. It's just a fancy topological name for the delta regular tree. So the point. So So you just take all the paths in the graph.
Yes, and it is known that the regular graph has spectral expansion to square root t minus 1.
The universal cover has.
Yes.
Yeah, and yeah, so and that's where the Ramanujan conjecture comes from. That there should be a finite graph with that, and yeah, we will see some of that connection. Okay, so yeah, so for this one, yeah, so a lot of it is sort of very careful account keeping, but the crucial thing is just this sort of back of the hand calculation we did earlier, back of the envelope calculation we did earlier. Actually, yes, you do the calculation on the front of the hand, right? So anyway, so and so this crucial thing is just this, and then you do it carefully. So this thing of going from delta to delta minus one happens in other settings also. So basically the same idea that you do the induction carefully in some and and after that so the nice thing here is this sort of thing of proving something more. So it's not just proving zero fitness, it's actually proving something about these ratios, and that is, so you have a stronger induction hypothesis. And so this actually, this idea of like writing down this induction and arguing carefully about roots using the idea of interlacing can be used to again prove the real rootedness of this polynomial directly without going through the map, etc. thing that we did earlier. That's in fact how Heilman and Lieb did it. And I wanted to do that to Posse today, but we couldn't. So let's see next time I'll do it, or you can just read the proof in the Heilman-Lieb paper. It's quite simple. I mean, the paper is very big and it has a lot of results. So if you want to read that proof, I can actually point you exactly. If you get the journal version of the paper, the proof is on page 199 and 200. So it's lemma 4.1 and theorem 4.2. So I'll just write it here. So carefully looking at interlacing, sign interlacing. At sort of, or maybe I should say sign changes. The sign changes using the same reference as above. Can be used to give a direct proof. Direct short proof of the Heilman-Lieb theorem of the real rootedness of the matching polynomial. And the reference for this is and see pages 190 and 200 in this paper. So the paper is from 190 to 32. You look at the pages 190 to 200. In particular, lemma. What is the lemma? 4.1 and 4.3. Okay, so that's it. So, if you have any questions,
So, are there some open problems regarding the matching polynomial, or more or less it's completely understood?
Open problems regarding the matching polynomial. I mean,
Or
the